So if you are watching this, it means that you survived for the first video about the introduction to artificial intelligence. This is part 2, and in this video we are to speak mainly about artificial intelligence history topics. So regarding the first industrial robot, this was developed by General Motors in '61. It was called the Unimate, and the team was led by Ralph Mosher, which is you can see here in the photo. There's a wonderful series about this topic. It was called the Frankenstein Temptation that I seriously recommend you to watch. Then in '64 we got Eliza. Eliza was the first chatbot. We could ask Eliza, or Eliza could ask us some questions about the health. It was a kind of therapist, and we can try this. You can try this by just using this link here provided here in the bottom. So in the '66 we got the first mobile robot developed by the team in Stanford led by Charles Rosen, and then we got a lot of multiple attempts to address and to solve board games with artificial intelligence. So this was like we got this example for Artwell Samuel in '66, and then we got the macaque later, and of course the Deep Blue versus Kasparov in 1997. So there is also several interpretations about when we have the so-called artificial intelligence winters. So in this graph here, we got, for instance, '66, the birth of the AI. And then we got this inflated hype. And then in the '80s, we got the first winter. And then new hopes. And then the second winter, and so on. We have in the right some important marks of AI over the time. So we can divide like the booms of AI in three parts. The first one they call it this GoFi, the good old-fashioned artificial intelligence, which was the main part is heuristic search, and we got here some use of artificial intelligence until the '60s, and then we got the first winter, and then we got boom 2 and boom 3. Boom 3. So I'm going to concentrate now first in this boom 1. Speak a little bit about heuristic search. What is an heuristic? Is the first question. And an heuristic may be a rule, a set of rules which help to solve a problem. It may improve the efficiency in searching for a solution. So we are going to address classic heuristics and modern heuristics in artificial intelligence, but here I'm just going to provide some classical examples of problems that we can use heuristics to solve them. The first one is called the water jug problems. And so we have two jugs, one with 4 liters and another one with 3 liters. And there is no marks in the jars, and the objective is to fill 2 liters in the 4 liters jar. So we want to have half of this filled. So we can only fill the jars from the tap, or put it into each other, and also to a drain. So these are the only possible moves that we can here. So the first thing that you can do is auto-formulate the problem. So the states here can be represented by these two variables, x and y, where x is the number of liters in the 4-liter jar, y is the number of liters in the 3-liter jar, so x and y. So the space state is represented by xy, where x can assume any of these values from 0 to 4 and y from 0 to 3. So the initial or start state, an objective or goal state, in this case the initial state is there empty, so 0, 0. And the final can be any of these, because we want to have 2 liters in the 4 liters jar, but it doesn't matter what is the quantity of the other jar, so you can be this one, this one, this one, and this one. Okay. So, okay, the moves, you can represent the moves from these conditions. I'm not going to go over this, but you can watch it if you want. And okay, so we want to find a solution to this problem, and not problema, by drawing the tree of states. And the tree of states for this case is this one. It begins with the 0, 0, then we can move for, okay, fill the 3 liters jar or fill the 4-liter jar. So we got the tree and we got here a solution. So we can go and search these three using different techniques. One is called the depth first search, which follows this line. So first we fill the 3-liter jar. This is not a right move. Then we pour the 3-liter jar into the 4-liter jar. We fill the 3-liter jar. We pour part of the 3-liter jar in the 4-liter jar. We empty the 4-liter jar, and then, okay, we pour the 2 liters in the 4 liters. This is the solution from the deep first search, and we got here a simulation from this solution. Okay, so they are empty. I fill the 3-liter jar, I pour the 3-liter jar in the 4 liters, then I fill the 3-liter jar again, which is this one here. So these are the 4, and this is the 3. And again, I move until I get the solution of 0, 2, okay? And then the 2, 0. So another classic example is these Hannoi towers, which is is a representation assuming that in the Buddhist temple in Hanoi there is a large room with 3 poles or 3 columns and 21 gold rings with different sizes. In the beginning, the 21 rings are all located, it should be here, in this case there are 21 in the left side, the left pole. So the monks, they just have to move the rings from this pole and to another pole, but they can only move one ring between columns at the same time, at a time, and the larger ring cannot overlap a smaller ring. So which is the solution for the 3 rings case? It's a simple case which is represented here. Okay, so in this case, okay, again we got the problem formulation, the states. In this case we got here the left, the center, and the right is the number of rings in the left, center, and the right columns. They can take one of these values. So the initial state is this one. They are all in the left pole. So the operator is to move a ring from a pole to another, and the objective state is to have all the poles in this form, in the right pole. Okay. So this is a simulation. Can here we move first this one, and this one, then this one, this one, this one for this, and we got the final solution. Okay. So this is the possible tree expansion. So in this case, for 3 rings, we have the minimum moves necessary to achieve the solution are 7 moves. So you can use this. So if you enlarge this number to 21, you can see the number of possibilities that you have to, the number of moves that you have to do, which is huge. So, and